For over 70 years, scientists have been baffled by astronomy's greatest mysteries. Why is the sun's corona, its outer atmosphere, millions of degrees hotter than its surface? The surface sits at about 6,000 degrees Celsius, but just above it, the corona blazes at over 1,000,000 degrees. It defies everything we know about heat flow. Until now, we've never had direct proof of what's causing this impossible temperature spike. Imagine standing next to a campfire. The farther you walk away, the cooler it gets. That's basic physics, but the sun does the opposite. Its surface temperature is around 5,500 degrees Celsius. Move outward into the chromosphere and it climbs to 20,000 degrees. Keep going into the corona and suddenly you're at 1 to 3 million degrees Celsius. This has haunted solar physicists since the 1940s. How does the temperature increase as you move away from the heat source? Something must be pumping enormous amounts of energy into the corona, but what? Theories have pointed to magnetic waves for decades, but we've never actually seen them until October 2025. Enter the Daniel K. Inouye Solar Telescope in Hawaii, the world's most powerful solar observatory. Its 4-meter mirror and cutting-edge instruments can resolve features on the sun just 18 kilometers across. That's like seeing a coin from 100 miles away. The telescope's secret weapon is called cryo-NIRSP, a cryogenic near-infrared spectropolarimeter. This mouthful of a name describes an instrument cooled to extremely low temperatures that can detect the faintest signatures of ionized iron at 1.6 million degrees Celsius in the corona. Using this technology, a team led by Richard Morton from Northumbria University detected something extraordinary: torsional Alfvén waves. These are twisted, corkscrew-like motions traveling along magnetic field lines, predicted by theory for over 50 years but never conclusively observed until now. Here's how they spotted these invisible waves. The team focused on thin coronal loops, arches of plasma guided by magnetic fields. Using the Doppler effect, they measured velocity shifts in the light from highly ionized iron atoms. On one side of these loops, the plasma was moving toward the telescope. On the other side, it was moving away. But critically, these movements were twisting back and forth in a corkscrew pattern. The smoking gun signature of torsional Alfvén waves traveling upward from the sun's interior. 3D simulations and corroborative data from NASA's Solar Dynamics Observatory confirmed what they saw. These waves carry enormous amounts of energy, potentially matching the energy transported by kink waves, another type of magnetic wave previously detected in the corona. The discovery provides crucial evidence for how energy travels from the sun's churning interior, up through the surface, and into the corona, where it's converted into heat. Why does this matter to us here on Earth? Understanding coronal heating isn't just academic curiosity. The corona is where the solar wind originates, a constant stream of charged particles flowing outward at hundreds of kilometers per second. When the sun releases massive bursts of energy through solar flares and coronal mass ejections, that superheated material can slam into Earth's magnetic field, disrupting satellites, communication systems, power grids, and GPS networks. These space weather events cost billions in damages and pose risks to astronauts. By understanding how the corona is heated and how energy flows through it, we can better predict space weather events. This means protecting critical infrastructure and advancing our ability to forecast solar storms, creating a weather forecast for space. Detecting torsional Alfvén waves represents a breakthrough in solving astronomy's longest-standing puzzles. Richard Morton's team, publishing their findings in Nature Astronomy, has given us the first direct proof of how magnetic waves might sustain the sun's mysterious million-degree crown. With the Inouye Solar Telescope operating at full capacity, we're entering a golden age of solar physics. Every observation brings us closer to understanding our star's complex behavior and protecting our technological civilization from its powerful outbursts. The universe's mysteries are waiting, and sometimes the answers are closer than we think, just 93 million miles away.